Okay, so let me see. Someone said something. Oh, hi Mary. So last time we went through this group discussion on some ideas for sensitivity analysis for various assumptions in for a method in an observational study, and I attended a lot of your group discussions, and I find a lot of interesting ideas. So we heard about assessing sensitivity for an unobserved confounder, or in other words, conditional ignorability. I have also heard assessing a sensitivity for example, the modeling assumption for the propensity score, or assessing sensitivity for modeling for the outcome regression, or assessing sensitivity against propensity, the positivity assumption. So these are all great ideas, and actually, if you dig deep enough, they will ultimately lead to publications, I believe. So today we'll look more carefully into sensitivity analysis, and what we'll be focusing on is sensitivity to unobserved confounding. In other words, violations to the conditional ignorability assumption. And before I forget, later this week, probably in the weekend or tomorrow, I'll send out a poll so that you can fill up the times you would prefer to do your final presentation. So remember, our final presentation would be in week 10, as well as a Thursday in the final week, final exam week. So there will be 3 dates, and you can discuss with your partner what dates you would prefer. But I would assume that everyone should be available on all of these dates, because these are times reserved for this course. So watch out for that email or announcement, I guess. Oh, by the way, when I write an announcement and post it on Canvas, will you receive an email or not? Can someone tell me?
Yes, we can receive the email.
Oh, okay, that's great. Thank you. Okay, so let's continue. So today we're going to focus on sensitivity analysis for unobserved confounding. So to be more specific, the question we're going to ask is how strong the effects of the unobserved covariate on the exposure or on the outcome would have to be in order for the analysis result to be changed. So this is the ultimate question that we're going to answer by saying sensitivity analysis. And it can be asked in multiple ways to operationalize this. And here are 2 ways to do it. So the first way is to ask how strong the confounder needs to be in order to change the significance or significantness of the analysis result. Right. So we may want to provide an answer of, the confounder needs to be such so that the originally significant result with certain p-value threshold becomes insignificant. So that's one way. Another way is to ask, what is the true causal effect? In other words, can you provide me an estimate and the confidence interval for the true causal effect, assuming a specific unobserved confounder level? So you notice that these two are a kind of related question, because from the second one, if you have the confidence interval, then you're able to calculate the significance of the analysis result. But nonetheless, these are 2 common ways to pose the sensitivity analysis question. So today's learning objective, the first one is to understand the general idea of sensitivity analysis. Then we'll go through in detail of one particular approach proposed by Rosenbaum. Paul Rosenbaum is a very important person, a researcher in causal inference. And we'll look at his sensitivity analysis approaches. Then we'll also briefly look at various other approaches for sensitivity analyses. So today's lecture will not be as detailed level compared to some of the previous lectures. but hopefully this gives you an idea of what sensitivity analysis is and a plethora of the tools that is available so that you're aware of them and be able to apply them if you encounter the need in the future. Okay, so to start, let's first look at this first sensitivity analysis that was done in the literature. It was done in the 1950s. So this is the scientific question: does smoking cause lung cancer? Now, this is a causal inference question, and another way to ask this is by saying, can lung cancer be prevented or reduced by not smoking? So the answer may be yes, maybe no. At that time, people don't really know the answer. So one might argue that maybe the higher rates of lung cancer among smokers are due to some other differences between smokers and non-smokers after accounting for the observed variables. So we now know that this question is about unobserved confounding between smoking, which is the treatment here, and lung cancer, which is the outcome. So this is R.A. Fisher, and he is known to love to smoke. So he had written something saying that he thought the observed relationship between smoking and lung cancer was due to some unobserved genetic factor that made people more susceptible to both. So in other words, he was defending that smoking does not cause lung cancer. So, these are arguments, but you can't really tell whether that's true or not, because this is about an unobserved genetic factor. So what a group of researchers did, led by Cornfield, was to do a sensitivity analysis for the relationship between smoking and lung cancer. So what they found is that this is the essence of the conclusion. So what they found is that if there exists such a genetic factor that explains this relationship between smoking and lung cancer, then this factor would need to be more strongly related to both smoking and to lung cancer than anything that is already observed, so any observed covariates. So what it means is that it's unlikely that the association between smoking and lung cancer can be completely explained by some unobserved confounder, because that confounder would need to be such a strong one, and therefore a causal relationship is plausible. Now, none of these is mathematical proofs. These are still arguments, but at least it makes it a little bit more quantitative. So let's see how it was made quantitative. What I mean by quantitative, by looking at this quote from their original paper. So what they wrote is that, thus, if cigarette smokers have 9 times the risk of non-smokers for developing lung cancer, and this is not because cigarette smoker is a causal agent, but only because cigarette smokers produce some kind of hormone X. So here you can kind of draw a causal graph, right? We have a smoking over here, we have lung cancer over here, and we may have an arrow between these two. Then this generating hormone X could be some unobserved variable U, and it can have an arrow pointing to A. And it can also have an arrow pointing to Y. So suppose the relationship is by some hormone, then the proportion of the hormone X producers among cigarette smokers must be at least 9 times greater than that of non-smokers. If the relative prevalence of hormone X producers is actually considerably less than this 9-fold that's needed to be, then this conjectured hormone cannot account for the magnitude of the effect between smoking and lung cancer. So what's important is that here they used a quantitative measure, 9 times. This is an important conceptual advantage. I should write advantage over here. or well, advanced. Yes, advanced is the correct word term. So why is that? Because it replaces a general qualitative statement by a quantitative statement. So what's the qualitative statement? The qualitative statement is that, the association between treatment and outcome does not imply causation because we can have unobserved confounding. So what is this quantitative statement that they proposed? This is that to explain the association seen in a particular study, here the relationship between smoking and lung cancer, one would need an unobserved confounder of a particular magnitude. So not just saying, there can be unobserved confounding. Here we're saying the unobserved confounder needs to be of certain strength. So why is that an advance? Because the qualitative statement, although true and it applies to all observational studies, is too general to be really useful. But here, the quantitative statement is made specific to a particular study. So because it's more specific, we can kind of make more sense of it in terms of the magnitude of the strength for the confounder. So today we're going to see how we formalize such ideas. Any questions up to this point?
Yeah, I have a question.
Yes.
Does the quantitative statement depend on what you think the DAG looks like?
Yes, it would. Yeah, and we'll shortly see what's the DAG we're going to work on today. But in general, yes. So I think one important point you hinted upon is that in order to make quantitative statements, we need to make assumptions. And the assumptions are, again, untestable because these are about the unobserved confounder. But nonetheless, this is one step towards being more specific. So we'll have a little bit more discussion about this towards the end of this talk, but a lecture. But yeah, that's a good question.
Yeah, I mean, the question is like, most of these I can already predict that most of these methods are going to just assume some sort of fork structure with the unobserved confounder. So the question is, how much wiggle room does that grant us to misspecification of the DAG? So, if the DAG looks like really weird, but we can say, well, it's close enough to a fork structure, then are we good? I mean,
good question. I don't have a complete answer to this question. What I can say is that, so at least you can, so although what we're going to see today mostly relies on supposing particular DAG structure, but these can still be useful at least in one direction. So this direction is the following. So suppose the analysis, assuming no unobserved confounder, assuming a conditional ignorability, suppose we reach at a certain conclusion. Then suppose we assume a certain DAG for the unobserved confounder, or in general, certain assumptions on the unobserved confounder. Then we find out that, the result is kind of sensitive with the magnitude of this unobserved confounder in this particular DAG that satisfies this particular structural assumption. Then I think it would be sufficient to conclude that the analysis result is somewhat sensitive. Now, to go the other way, if we assume a DAG and it turns out under this particular DAG the study analysis is not sensitive, it's harder to argue that it's indeed not sensitive because you could have other DAGs, you can have other assumptions for the unobserved confounder. So that's kind of a long explanation of what I said, that it's still useful at least in one direction. Does that?
I think, yeah, that makes sense to me. That's a good approach.
Okay, thank you. Any other questions? Okay, so now we'll see the DAG. So this is the notation and the setup for our discussion today. And throughout today's lecture, I would actually encourage you to pay attention to what are the assumptions that we're making for the unobserved confounder. So we'll use X to denote the observed pretreatment covariates. We'll use U to denote an unobserved variable, presumably the unobserved confounder. Although from previous lecture, we kind of dissed the idea of defining a confounder, but in general, we care more about confounding. But anyway, we'll use the term that U is an unobserved confounder. It's definitely the case in this simple DAG, at least, right? So we have this backdoor path between A and Y that goes through U. So using backdoor criterion, we know that we should be blocking U in order to get conditional ignorability. Now here I also have an arrow between U and X, and the direction, whether it's from U to X or from X to U, that doesn't really matter for our purpose. So, but I'm just including this arrow for generality, I'd say, because otherwise you can think of U as the part, you can think of U, redefine U as subtracting the part that's correlated with X. I'm using the term subtracting loosely, but that's one other way to conceptualize this thing. So our assumption for today is that suppose we have conditional ignorability given X and U, but not just given X. But since we don't observe U, we'll proceed to do analysis pretending that X is good enough for conditional ignorability. Then we get an analysis result. Then we see what's U's impact on the correctness, on the validity of that analysis result. Okay, so now let's talk about this Rosenbaum's approach. So here this is the same DAG, but I'm just omitting the arrow between U and X to give me more room to write stuff. So in general, Rosenbaum's approaches, we'll see a few approaches short after. They're interested in finding the threshold of the associations between U and A and U and Y. That would render the test statistic of the study insignificant. So there are a few pieces of information from this general description. So one is that the quantity that we'll use to characterize the unobserved confounder is you can think of the strength of these two arrows. I'm writing OR to be the odds ratio because you will see that we'll be considering the special case of binary U and binary Y. But in general, you can think of these as characterizing the correlation between the two, and the correlation between these two. That's information number one. These are the measurements for the unobserved confounder. Or I guess measurements for the strength of the unobserved confounder. The other important message is that Rosenbaum's approach focuses on the test statistic, and in particular, the significance or insignificance of the test results, so the p-values. And we'll see how that's used in this approach. Okay, so Rosenbaum's approaches can be categorized into, I guess, 3 approaches. These are very intuitive. So I'll start with the simultaneous approach. This is a general description. So we'll use a gamma to describe this association. We'll use a delta, another parameter, to describe this association. Then we'll see when we vary gamma and delta, how does the p-value of the analysis result change? That's the simultaneous approach. Then, after understanding this, it's much easier to understand the primal and dual. So for the primal approach, we're assuming that the correlation between the unobserved confounder U and Y is perfect. So odds ratio equal to infinity. And we are only varying the association between U and A and see how the p-value changes. And for the dual, it's flipping the role of these two arrows. So as a preview, we'll look carefully into how one would conduct a primal sensitivity analysis. And we'll touch briefly on the simultaneous approach. Any questions?
Is the,
Okay.
I mean,
Yeah.
does it make sense to think about variables that are perfectly correlated with something you've observed? That, like, is that a practical approach?
Good question. I don't think that's a practical assumption,
Okay,
but that's kind of an extreme case that gives you the. You can think of that as giving you the bound of what would actually happen.
sure. Okay, that makes sense.
Yeah.
Yeah.
Okay, good question. So yeah, now let's look carefully or closely at the primal approach. So let's see how do we actually operationalize the ideas that we draw on the graphs. So suppose we have two units. We have a collection of samples. And suppose we have two units, J and K, with equal covariates. Observed covariate value, but different unobserved confounder value, different U. So we use Pj to denote the probability of receiving treatment for J's person, and Pk for kth person. Now we can write this odds ratio for unit J versus unit K getting treatment. If we have unobserved confounder, if we have conditional ignorability, then we usually have Pj equal to Pk, right? The propensity score only depends on X, or the randomization probability only depends on X, so that we have this odds ratio equal to 1. Now, this is not always correct, so that's why I write usually. Even when the treatment assignment is unconfounded, we can also have cases where Pj and Pk are not equal to each other. So you can, I'm not telling you what it is right now because that's not very important for our discussion, but also I think it might be interesting for you to think about this on your own if you can find a counterexample. That's a fun exercise. But anyway, this usually is the case, and I think intuitively you would agree with me. Okay, so now if the treatment assignment is confounded, then it's possible that this odds ratio does not equal to 1, right? Maybe treatment assignment also depends on you, so that these two individuals, they have different treatment assignment probability. Okay, so we see that odds ratios like this can be used to characterize the magnitude or whether there is unobserved confounding. So let's be more precise. So here is the odds ratio between treatment A and unobserved confounder U. Let's suppose that U is binary. We'll be more specific. Formally claim that we assume U is binary shortly, but here you can pretend it is. So for odds ratios like this with equal covariate value, we can put a bound on this. Suppose for some gamma greater than or equal to 0, we have this bounded by gamma inverse and gamma. So the interpretation of gamma is the following. If gamma equal to 1, then those with the same x has the same probability of receiving treatment, which pretty much translates to unobserved confounding. If gamma equals 2, for example, now you can say, oh, gamma, if this always equal to 1, we can also have gamma equal to 2, and the inequality holds. That's true, but let's suppose that when gamma equals to 2, there are cases where this equality is met. So in this case, if gamma equal to 2, two units with the same x could differ in their odds of receiving the treatment by as much as a factor of 2, right? So in other words, this gamma measures the degree of potential departure from a study that is unconfounded. So that's the use of this gamma. Now, I'd like to introduce a different but equivalent view of characterizing the magnitude of unobserved confounder. And I think this also provides some intuition. So let's forget about what we just saw. One other way to introduce unobserved confounder is to express the log odds of the treatment assignment probability to be a unknown but flexible function of the covariates and an additive term of the unobserved confounder. So this explicitly says that U affects the randomization probability or the treatment assignment probability. Okay, so now for two individuals with equal x, we can calculate this odds ratio again, and it equals this, e to the gamma uj minus uk. So here I'm just rewriting the last sentence from the previous page. So what this tells us is that units with similar x will differ in their odds of receiving treatment due to difference in u. Now, one can actually show that this way of incorporating unmeasured confounding and the previous one with the capital gamma that's bounding the odds ratio of the treatment assignment probability, these are equivalent. And the equivalent has quotation marks because you kind of need to be mathematically more careful to define their equivalences. So the precise statement of this equivalence result and the proof, you can find it in this book. And I just tried. We will be able to download it via UCI's library. So you can take a look if you're interested. But the main message here is that we can use either formulations to characterize the strength of the unobserved confounder by considering how strong it's correlated with the treatment assignment, how much influence it has on the treatment assignment. Okay, so now suppose we characterize the unmeasured confounding by this gamma, or by this little gamma. They're equivalent, as we see. So the next question is, how does the p-value of the causal analysis depend on gamma? Right? And this was the question that Rosenbaum's approach tries to answer. Now, when we say p-value, we need to define a particular analysis method we're using, right? What coefficient we're looking at and what p-value for what. So now it turns out that how does the answer to this question is very dependent on the particular analysis methods. And a general discussion for a variety of methods, you can look them up in this reference. For today in class, we'll consider a very simple example to make the idea clearer. So this is the setting that we'll consider for the primal approach. So we'll look at one-on-one matched sample, propensity score matching, for example. We'll look at binary outcome. We'll look at a binary confounder that is perfectly correlated with Y, because we're looking at the primal approach, right? This is an extreme case. When it's perfectly correlated with Y, how much of a correlation do we need it to have with a treatment assignment in order to significantly change the analysis result? So this is the setting, and the analysis method we'll look at is a non-parametric test called McNamer's test. I'm not sure if you have studied that in your other statistical courses. If not, that's okay too. We will go through some of the brief ideas so that you have enough intuition to understand what's going on. And I'll also provide detailed references for detailed mathematical derivation. Okay, so all clear about the setting that we're considering?
Yeah, the reason you're using maximum is because it's a binary outcome.
Yes.
Is that why? Okay.
Yes.
Okay, just to clarify. Thanks.
Right. Okay, so we'll look at this motivating example for quite a few methods today. So let's go through it. This is a study done in 2010, and they try to answer the question: does maternal suicide, so someone's mom died of suicide, does that lead to offspring's risk of hospitalization for suicide attempt? So here, the treatment A is whether the mom committed suicide, and the outcome is whether the child themselves, instead of committed suicide, get hospitalized for suicidal attempt. So that's a nuanced difference, not very important for our discussion. Okay, so what the researchers did was to do a one-on-one propensity score matching. So they looked at the data from Sweden in longitudinal population-based registries from 1973 to 2003, and they identified 5,600 offsprings who lost a mother to suicide. So these are all the you can think of them as treated individuals. So in order to find match, they also look at what could be as a good control match, good control. So they considered offsprings who lost a mother to an accident. So they also lost a mother, but not to suicide, but to accident. And they used this to form this one-on-one propensity score matching. And the idea of finding matches in this population is so that we can tease apart the effect of mother died from the effect of mother died because of suicide, so that they can, this affects the way they are interpreting their result. I guess that's the thing I'm trying to say. Okay, so among these 5,600 treated individual, 233 of them get hospitalized due to suicidal attempt. And for the 5,600 control cases, 128 of them got hospitalized for suicidal attempt. So this summarizes the outcome that we have. Okay, so one can calculate the odds ratio. This is a binary outcome, binary treatment data, right? You can calculate odds ratio in the matched sample, and this is the result. So we see that it does not cover 1, so it's statistically significant. So this is analysis assuming no unmeasured confounder, right? After matching, we have as if simply randomized experiment. Now, to do a sensitivity analysis, we will want to know, would potential unobserved confounders such as genetic predisposition to suicidal behavior influence the results? So here's what the researchers did. So again, this is a presentation of the data. So we have, let's see. So we have each of these cells are the counts for pairs. So this is a 2x2 table. This is a 2x2 table, and let me just briefly explain what it means. So remember, we have 5,600 matched pairs. So for example, this number 7 here means that among all these matched pairs, there are 7 pairs such that for both individuals in this matched pair, both of them attempted suicide. And this cell means that we have 121 pairs in which the maternal suicide, that would be the treated individual. So among these 121 pairs, the treated individual did not attempt suicide, but the control individual attempted the suicide. And similar here, 226 is treated individual has y equal to 1, control individual has y equal to 0. Okay, so this summarizes the data, right? There's no covariate in here, but one would argue after propensity score matching, if that's if the propensity score model is correct as specified, blah, 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 then we don't have to adjust for covariates. I mean, you can, but you don't have to. Okay, so this is just reiterating what I've been talking about. So we have these off-diagonal pairs where exactly one of the two offsprings, one of the two individuals in the matched pair, hospitalized for suicide attempt. So for these matches, each of the match, they differ in their two outcomes. So they're called discordant pairs. And here, I think I should write 2. Right, it should be 226, not 266. But anyway, this is kind of describing what I just said. Any questions? Okay, so let's see. So how would one calculate the p-value for testing a no causal effect? Previously we said, oh, you can calculate the odds ratio and do the confidence interval, etc. But here so that's one way to do it. Here, in order to facilitate the discussion of primal analysis, we'll look at I'd say related, but slightly different idea. So this is called a randomization test. We did not talk about randomization test in this class up to this point. And I won't be going into details about it. So mainly I just try to provide you with some intuition. But if you want to know the details behind these kind of tests, which are classical ideas in causal inference, you can look at these references. Okay, so here's the idea for this hypothesis test. So in the matched sample, we know that treatment is as if randomized if we have no unmeasured confounding. So therefore, if we are testing for no causal effect, right? If this is our null, then under the null, the outcome for those with a equal to 1 and the outcome for those with a equal to 0 should be similar in each matched pair, because no treatment effect. And therefore, under the null, we can randomly permute the label of a equal to 1 and a equal to 0 without changing the distributions of the outcome under treatment and outcome under control, where these conditionals are the permuted labels. So intuitively, I think it makes sense because we have no causal effect under the null, and we have randomized treatment assignment. So you can just change them as you wish, and they shouldn't change the marginal distribution or the conditional distribution of the outcome. Okay, so what that means is that the off diagonals here should be similar to each other under the null, because these are the cells or the pairs where these are the concordant pairs. In other words, these are the pairs where the outcomes under treatment and outcome under control are different. So if we have the null, then we can randomly permute the treatment assignment within each pair and still have similar results. So, and therefore, these off diagonals should be similar to each other under the null. Now, of course, from here you can see they are different from each other. But how different is different? You can imagine that for each permutation of the labels, the treatment assignment labels, you can observe such a 2x2 table under permutation. Now, the p-value means the probability of getting the result you observed as or extreme, getting the result as or more extreme than the actual result you observe. So you can do many times of permutations and calculate the proportion of times where you get a result as or extreme as this. And that would be the p-value. So this is formalizing, or I guess more comprehensively saying the thought process that I just described. So and to formalize it, you can actually use this thing called McNamer's test to test this 2x2 table. So the equality of the off-diagonal elements. And it turns out that the p-value is very small, less than 0.0001. So it means that we have strong evidence that maternal suicide leads to offspring's hospitalization for suicide attempt. Now, so far is analysis under unmeasured confounding. So how much unmeasured confounding? So far is the analysis under no unmeasured confounding. Now the next question is how much unmeasured confounding would there have to be to alter this conclusion? So what we can do is that given a value of the big gamma, remember gamma captures the correlation between the unobserved confounder and the treatment. So given a value of the gamma, one can calculate the upper bound on the probability of receiving treatment and the lower bound on the probability of receiving treatment. Right, you can just invert the odds ratio formula to get these numbers. And because we're doing a primal analysis, we're assuming that U is perfectly correlated with Y. And therefore, we can use these new randomization probabilities to again calculate or do the hypothesis test to get the bounds on the p-value. Right? Because these are bounds on the probability of receiving treatment. So because these are bounds, using these numbers to calculate the p-value, these will be the bounds on the actual p-value. And therefore, we have translated a gamma to a p-value under the gamma. I hope you're following the logic. Now, the detailed derivation of, for example, what forms would these be, how to calculate the p-value under these randomization distributions, you can look up this paragraph. Okay, so now one good thing about this is that because it's been around for a long time, this is a very popular method. So there are actually not just R packages, but Excel spreadsheets that you can use to do this kind of analysis. So I'd like to show you quickly what this looks like. So you can download an Excel spreadsheet from the link on the previous page. And this is the spreadsheet. So what you will input are these cells. So these are the counts of the observed data, right? The 2x2 table. And the spreadsheet automatically calculates all of these other values. And in particular, we could check that, for example, for gamma equal to 1, meaning that no unobserved confounder, then the p-value should align with the p-value that we calculated, which is almost 0. That's observation number 1. Okay. Then observation number 2 is that we see as the gamma increases, the p-value here, we're looking at the two-tailed p-value upper bound. The p-value increases as well. You see that the p-value goes to above 1 and goes to 2. That's just how the program is set up, because this is calculating two-tailed p-value, and it's not, well, when you have the extreme, you're calculating the entire probability distribution twice. So you have p-values greater than 1, but that doesn't really concern us because we won't be interested in these cases. The important thing to observe is that when gamma equals 1.5, the p-value increases to 0.04. Oh, I'm sorry. And when gamma equals 2, the p-value is, so you can think, in this case, it should be 1. So which means for a gamma value between 1.5 and 2, there should be a situation where the p-value equals 0.05, which is the significance level that we care about, say. So you can play around with this number, you can insert a number, and it gives you a p-value. And it turns out that when gamma equals 1.509, the p-value is almost 0.05. So this is, I just described a procedure of using this Excel spreadsheet to do this sensitivity analysis to get the gamma that changes the significance level. So this is just essentially what I was talking about on the previous page. Okay, so now we find a gamma that leads to a change in the p-value. How to interpret it? This is one way to interpret this result. So in this motivating example, to attribute to the higher rate of offspring suicide attempt hospitalization to an unobserved covariate, rather than to an effect of the treatment, here mother died from suicide, that unobserved covariate would need to produce more than 50% increase in odds of maternal suicide. So translating into mathematical notation, this U needs to produce more than 50% increase in odds of A equal to 1. And it would need to be near perfect indicator of offspring suicidal attempt hospitalization. So near perfect correlation between the U and the Y. This is essentially translating the math into English language. So this is called moderately sensitive, but I just copied this sentence from one of the papers I read. Since one can argue in different ways, right? Well, does 1.5 mean moderately sensitive, very sensitive, not so much? One can argue different ways. And towards the end of the lecture, we'll see how to make more sense of this 1.5 or 50% increase in a specific study. So we'll see shortly, but for now, bear with me by saying this. Any questions? Okay, so now we've looked at the primal approach. This is a reminder of the three approaches. The dual, you can imagine this is very similar. You just switch the role of these two arrows. So then we'll look at briefly the simultaneous approach. We won't go into detail about the math, but the general ideas. Okay, so in the simultaneous approach, instead of varying, so here it should be an A, it shouldn't be a T. So because in an older version of the note, I use T to denote treatment, but we have been using A, so it should be AU. So in this simultaneous approach, we vary both the odds ratio between treatment and the unobserved confounder, and the odds ratio between Y and the unobserved confounder. So this kind of helps to answer Isaac's earlier question, right? If we only vary both, then maybe it can be a more plausible situation. So now, again, we can calculate the P plus and the P minuses. And as before, but I mean, their meaning are as before, but now they will need to incorporate both gamma and delta. So you can look at this paper for detailed derivation for these formulas. But anyhow, the logic is that we have parameters characterizing the odds ratio or the magnitude of the unobserved confounder. And from that, we can then translate these parameters to a p-value. So this is what a result would look like. So this is just applying this simultaneous approach to our motivating example. So, and because we have two tuning parameters, we have a table of p-values. So this means when gamma takes certain value and when delta takes certain value, what is the p-value or the bound on the p-value that we observe, would observe. So this is a way to read this table, and you can see that well, p-values that are kind of larger than 0.05 or close to 0.05 are highlighted over here. And it's reasonable that these are the highlighted ones are all on the lower right corner of this table, because the more to the right or the more to the lower, we have stronger unobserved confounding. Any questions?
I have a question.
Yes.
So for this table, I guess the last row or the last column where one of the two parameters is infinity corresponds to primal or the dual situation. Is that right?
Yes, right.
Okay, thank you.
Okay, yeah, and you can see, for example, here is 0.75 when gamma equal to 2, and infinity is, here is infinity, so primal, right? Remember 0.75, we have a similar number here. We have 1.4, which should be divided by 2, because it's double calculating the p-value. So it's close to 0.75, although I think maybe they used some slightly different algorithms. But at least the scale lines up. But yeah, that's a good question. Okay, so to summarize Rosenbaum's approach, these are mostly easily implemented when using one-on-one matching, and we have seen a particular example with one-to-one matching. But as I mentioned earlier, there are ways to do more general settings. And what we have seen is that we can use a non-parametric test and calculate the p-value or the bounds on the p-value under a hypothetical unobserved confounder. And the whole idea of Rosenbaum's approach is to examine at what point, for example, what associations of U with A or U with Y the result would change. How much can we push the confoundedness in our hypothetical situation? So next, we'll talk about a few other approaches that rely on a similar general idea, but produces different sensitivity analysis results. So instead of p-values, they look at other things. Okay, so some other approaches. Now, this will be very brief, as you'll see, mostly 1 or 2 slides per approach. And the purpose is that you know what's out there, so that when you need them, you can find them. Okay, so this is what we said before. Rosenbaum's approach focuses on statistical significance. The following approaches generally aim to obtain an estimate of the true odds ratio, and sometimes the confidence interval as well, accounting for a hypothetical U. So there are trade-offs both between Rosenbaum's approach and the approaches that we're going to see, but also among these approaches. So they will rely on different assumptions, and some need to specify more parameters or have more assumptions about the distribution of U. So we'll see shortly. Okay, so the first other approach we'll see is this method proposed by Schneeweis. I looked up the pronunciation today. Apparently, this is a German name. So one approach proposed by this person is called rule-out approach. And the idea is to find a point at which, again, here should be an A instead of T. Find a point at which the two correlations that captures the magnitude of the unobserved confounding makes the true odds ratio equal to 1. This should be Y and A. This is the causal odds ratio, causal effect that we care about. So in order to do this, we will need to specify the prevalence of U. So not just how U correlates with treatment and outcome, but also what's the distribution of U in the population. So you can see that this is a more conservative approach in a way that you would need a larger odds ratio here to make the true odds ratio equal to 1. Because the approaches we looked at before is essentially having the confidence interval for the true odds ratio cover 1. Right? So here you see this one is a more conservative approach. Now there's this other approach called array approach, which summarizes the impact of the unobserved confounder U using a bias factor. So the bias factor is calculated this way, but I don't really, I'm not going to go into details about this. The key message is that these are the things you need to specify. The prevalence of U among treated, the prevalence of U among control. Remember, this is still a binary unobserved confounder, and these odds ratios. Then the true odds ratio can be calculated by this quantity. So divide the observed odds ratio, the observed causal effect, the causal effect calculated from the observed data pertaining no unmeasured confounding, divide that by this bias factor. And a nice thing is that you can also use Excel to do these. It's very fascinating to me that there are Excel spreadsheets to do these sensitivity analyses, but maybe there are also Excel spreadsheets to do like inverse probability weighting, etc. But I guess that's harder. So I'll make a related comment to this towards the end of the lecture. So that's two of the approaches proposed by this person. We'll see a few more approaches, and mainly to get a flavor of what's out there and the assumptions that you need, or the inputs you need to have for these procedures. So this is an approach proposed by Danyu Lin, and they were summarizing the impact of the unobserved confounder using an so-called adjustment factor, which is calculated this way. And again, you're able to see what are the parameters they need for their sensitivity analysis. So you need the prevalence of the unobserved confounder on the treated, on the control, and you need this kind of association between U and Y among treated, and association between U and Y among control. So you see that they also require a bit more compared to Rosenbaum's approach. And again, the true odds ratio then can be calculated by doing this adjustment. So you can use these adjustment factors to adjust the confidence intervals as well, it turns out. And we went through from this expression, these are the parameters that you would need to specify to use their approach. Okay, so here is one other approach. Similar ideas appear in both papers, but slightly different. But the main idea is that we, with a hypothetical unobserved confounder, we can recreate the data as if U was observed, if we assume enough distributional relationship between U and the other variables. So again, we're looking at a binary outcome and a 2x2 table. So, so this would be the original data, right? Without thinking about U, this would be the original data. Of course, not thinking about covariates as well for simplicity. But if we know U, we can break this data, this table into two small tables. This is the 2x2 table under U equal to 0. This is the 2x2 table under U equal to 1. And of course, in order to do that, you need a lot of assumptions on how all these variables are correlated with each other. And again, T's here should be little a. Okay, so this is one other approach. And hopefully, intuitively, you agree this might be something that you can do. So now let's see, how does these approaches compare with each other? Okay, so this is a table showing the combination of this odds ratio and this other odds ratio. And I'm specifying some additional things since they would need other quantities as well. At which the inference for the motivating example changes. So non-significant p-value p-value changing from significant to insignificant, or for example, the rule out approach, the true odds ratio from not equal to 1 to become equal to 1. And we see that all these approaches, because they rely on different parametric assumptions on the unobserved confounder, they output different results. So we will discuss their differences in two slides after. But first, let's ask a question that's related to something we previously see. So for example, here we have 1.5. And I said that it's moderately sensitive. What does it mean? How do we actually interpret any of these odds ratios in a meaningful way? How large is large? How small is small? One way to interpret these odds ratios is, or any measurements or strength of the unobserved confounder, is through comparing that to the observed variables. So for example, here we are plotting the two odds ratios for the observed confounders, the observed covariates. So for example, here we see that this covariate is correlated with the treatment assignment with an odds ratio of 5, and is associated with the outcome with an odds ratio of 1.4. So by comparing to the odds ratio of observed confounders, we're able to tell, oh, if we have a unobserved confounder with certain strength to change the analysis result, then this unobserved confounder needs to be at least this strong. For example, from the previous page, we have 1.5 and infinity, right? Here is 1.4 and 5. So this unobserved confounder needs to be at least as strong as this one in terms of association between the treatment and the outcome in order for it to change the analysis result. So this puts some context on the absolute value of the odds ratios. And therefore, you will be able to use this kind of context to discuss with the researchers. So the domain scientists that you're working with, right? You can ask them, do you think there will be a unobserved confounder that's as strong as this particular variable, etc.? So you can have this kind of discussions. Okay, so now we go back to look at to discuss some of the results that we see. So The first row, Rosenbaum's primal approach, indicates most sensitivity. That requires an odds ratio of 1.5 to alter the result. And that's in part because it's assuming a perfect association between u and the outcome y. Now, this rule-out approach indicates the least sensitivity, as we see here. The rule-out is 4.4 and 10. And that's because, as we said earlier, it's conservative. It's looking at not just the confidence interval contains 1, but the actual point estimate is equal to 1. So that requires a lot more stronger unobserved confounder to achieve this. But in general, one might say, okay, these indicate moderate robustness to an unobserved confounder. I mean, this is not substantiated, so maybe you don't want to believe in this sentence. The more meaningful interpretation, what I said, should be from this graph when comparing to other variables. Okay, so now that we have seen tons of approaches, how do we decide between these approaches? One way to decide between them is from their different applicable situations. So this is a flow chart where you can follow to find out which sensitivity analysis methods you want to use. And I'll go through it briefly on the next slide. So first, you want to see if you have a one-on-one matched design. If you do, then Rosenbaum's approach would work. If not, maybe you want to find some other methods because Rosenbaum's approach is easiest to implement in a one-on-one matched design. So the next is your outcome binary or continuous. The non-Rosenbaum approaches that we discussed so far generally assume binary outcome. And the third, what's the target of interest for the sensitivity analysis? Do you want to see how strong the unobserved confounder is to change your significance result? Or do you want to see how does the unobserved confounder affect your odds ratio, in other words, your causal effect estimate, and maybe with confidence interval? And finally, you might want to ask, how much do you want to specify about the unobserved confounder? Can you assume a prevalence for it? Can you assume a prevalence for u under a equal to 1 and under a equal to 0? Or do you only want to specify the odds ratio between u and the treatment and u between the outcome? So these are considerations to help you to choose the particular method you want to use. So now you might want to ask, what if I'm in a situation where the previous methods don't cover? So usually it gets more complicated if we want to think about, for example, multiple unobserved confounders or a non-binary unobserved confounder. Because when thinking about multiple unobserved confounders, we need to consider their correlations with each other and their relationships with the treatment and the outcome. So we have multiple dimensional distribution that we need to specify. So one way to think about this is to think of the single unobserved confounder u as a conglomeration of a collection of unobserved confounders. Now, this may or may not work for your particular DAG, because sometimes if your DAG is of specific forms, you can't really deduce multiple unobserved confounders into a single one. But nonetheless, this might be a starting point. So similarly, thinking about a non-binary unobserved confounder can be more complicated. And because it's unobserved, you will always need to conceptualize maybe the meaning of it. So whether it makes more sense to think about something that's binary or think about something that's continuous. But anyway, if it's non-binary, you will need to make more assumptions about the distribution and how it relates to all these other variables. So finally, I'm going to provide you 4 more approaches. mainly with references so that you know what's out there. These are more general approaches for general U unobserved confounder and for general outcomes. But as you see, they require even more parametric assumptions. So for example, this paper in 2011 proposed a general approach for any type of U and any type of Y. But if you read that paper, you will see they require a lot of functions that need to be specified by the researcher. And they discuss how you're able to simplify things in special cases. So that's one other approach. There's another approach for sensitivity analysis for marginal structural models. So we have studied marginal structural models in this class in quite some detail. And here's a way to do sensitivity analysis for it. And in particular, they propose to quantify the unmeasured confounding through this function C, which depends on treatment and observed covariance X, where C is defined this way. So for example, let's look at the first row. This is expected Y0 given A equal to 0 and X equal to X. This is expected Y0 given A equal to 1 and X equal to X. So you can immediately see that if we have unobserved confounding, these two terms should be equal, and this quantity is 0. And similar here, if we have unobserved confounding, we can remove A equal to 1 and A equal to 0 in the conditioning, and these two will be equal. So how differently they are from 0 kind of captures the magnitude of unobserved confounding. And in their paper, they considered six functional forms for this particular unmeasured confounding magnitude function. If you're interested, you can you look at this paper. Okay, 2 more approaches and I'm done, I promise. So there is also, you can imagine there will be ways that you can use simulations to assess the sensitivity for unobserved confounding, right? As long as you're able to specify certain distributions, you can just run simulations to see how sensitive your results are. Under each simulation, how does the result change? So this paper does exactly that. They use the simulation and MCMC approaches to do sensitivity analysis. Now, this is a rather recent development in 2017. And these authors proposed a new way to summarize sensitivity analysis results called an e-value. So as we've seen previously, we've been using either an odds ratio, a single odds ratio, or a table with various odds ratios and different p-values to summarize the sensitivity analysis results. Now, these can sometimes be difficult to communicate. So it would be useful to be able to summarize the sensitivity analysis results just like a p-value that people use to summarize the significance of the results. Now, of course, there are debates around whether p-value is an appropriate measure for scientific evidence, but if we do not get into that rabbit hole, then we might agree that this is at least something that's easy to communicate. So if we're able to find something that's easy to communicate for sensitivity analysis results, that would also be a nice thing. Okay, so to summarize what we've seen today, in an observational study, the motivation is that you can never be sure you have measured all the confounders. So there is always this concern of unmeasured confounding. So what we can do is to do 2 separate analyses. The first analysis is to account for observed confounders using the methods we discussed in this class, like the IPW or propensity score matching, etc., assuming conditional ignorability given the observed variables. Then the second analysis one might do is to assess sensitivity to unobserved confounder. So today we looked at many different approaches that we can use to assess sensitivity. And the advantage of the sensitivity analysis is to help address concerns about unmeasured confounding. Maybe sometimes not address concerns, but to magnify the concerns if you find the results very sensitive. But nonetheless, it provides a more precise statement about how much a problem unmeasured confounding might cause. So doing sensitivity analysis is usually better than not doing it. Okay, so there are still many methodological challenges for sensitivity analysis in causal inference or in statistical literature. And as you've seen in today's methods, a lot of these methods require the researcher to specify parameters to characterize the unobserved confounder and its relationship with other observed variables. And as you see, when we move from Rosenbaum's approach to these other approaches, which generates confidence intervals, and to this even more general approaches that handles general types of confounders and outcomes, the more general the setting, usually the more parameters you need to specify. So if you want to be general, you want to have good scientific knowledge, good domain knowledge to be specify these parameters in a plausible way. Another challenge is that the reporting and interpretation of sensitivity analysis could be challenging. So today we've seen that we can use tables or figures so that we kind of be comprehensive about the sensitivity analysis results. But they can take a lot of effort to communicate, especially if you're writing, say, if you're writing a scientific paper. Now, on the other hand, single number summaries, such as odds ratio equal to this, p-value changes. This will be a single measure summary. These can be tricky to interpret because, again, it relies on a lot of other assumptions that you need to explain. So how to convey the analysis of sensitivity, the results of sensitivity analysis? That's another challenge. And in my view, this sensitivity analysis is an area that's very important, but relatively underdeveloped in causal inference literature. So with that, that's all we are going to see for sensitivity analysis. Any final questions before I let you go? So if no questions, as I said at the beginning, I'll send out a poll for your time preferences for your final project presentation later this week. So look out for that. And I will be around for additional questions or discussions. So yeah, you're dismissed. Thank you for coming.